Hey folks, we are on part 2 of lecture 9.2, all about pH. So we spent a lot of time looking at the relationship between H3O plus concentration, which is hydronium, and the OH minus concentration, hydroxide. And now we're going to look at the relationship between those concentrations and pH. Okay, so here's the full figure. I cut off the leftmost column previously when I showed you, but now here's pH. So remember we saw this part before where we see the relationship between H3O plus and OH minus. And now we have pH. And maybe you can see a relationship with these numbers as well. So for now, I'm just going to point out some spots along the pH scale. It goes from 0 up to 14. And let's see, remember we said human blood is 7.4, so it's marking it here. Saliva was slightly less, so it's marked towards more acidic at about 6. Some other things to consider, cola, yes, cola that you drink has a pH of 3. Orange juice is around there as well. HCl, gastric juices, battery acids are way up here at very low pH. Baking soda, milk of magnesia get higher. Some cleaning products, household bleach and ammonia are up at around a pH of 12, and sodium hydroxide is a very, very basic. Okay, so do we see a relationship yet between the pH values and something having to do with H3O plus? Well, I'll let you keep thinking about that as I first am going to have just a conceptual question. Select the correct statement concerning pH. So read these for yourself. You can pause it, come back. And welcome back. After reading through these, you discovered that low pH levels mean high acid concentrations, right? Okay, now let's look back at this. So the pH value is equal to the exponent in the H3O plus concentration, but it's a positive value, right? These are all small concentrations. pHs are all positive values, so the 4 in the exponent becomes a pH of 4. So the way this works out mathematically is that pH is equal to the negative log base 10 of the H3O plus concentration. Right, so that basically means log of the concentration, like on your calculator, you could take the log of something, right, is what do you have to raise 10 to the power of to get this number? And so in this case, it's really easy, right? 10 to the negative 4. What power do you have to put 10 to get 10 to the negative 4? Well, you have negative 4, right? And then we take a negative of that number to make it positive. So if you take in your calculator negative, which is usually not the minus, usually not the minus button, it's something like this or like this on your calculator. So take negative log, input the concentration, and you get pH. There is a review of logs on page A6 of Appendix A, and it's specifically about using the TI-30XA scientific calculator, which I know many of you have, and I recommend. So we see that just quite simply the relationship there is negative log of H3O plus. Okay, let's look broader at like the whole spectrum again, and the fact that this is a log here makes a really big difference in how this looks. Okay, so we could break out like, from 0 to 14, and if we look at like, the difference between a pH of 2 and a pH of 3 sounds pretty small, right? It's like, it's just one pH value. But it's what we call a log scale, right? Where actually every step here is a factor of 10 because we're taking base 10 logs. So 1 pH unit represents a 10x change in the hydronium concentration. 2 pH represents 100 times difference, right? And 6 pH is 1,000,000 times, or 10 to the 6 difference in the hydronium ion concentration, right? So you think about the range at which people can die from like acidosis or alkalosis, and it's like a 6.8 to an 8, right? Which doesn't sound like very much, but that's 1.2 pH units, which is over 10 times different. Okay, it's not 12 times different, by the way. It's 10 and then plus 0.2 towards the way to 100. So it's closer to like 30 times difference. Also interesting, just some of the other things on this slide, which I believe I took as a screenshot from Crash Course Chemistry. I don't have it referenced here, but I'm saying it, right? Crash Course Chemistry has great visuals sometimes, and so we can see the range of things. But even this is kind of probably not quite precise enough because it's in 100x chunks, right? From 6 to 8 is 100 times difference, and 8 to 10 as well. But even citrus juices are down here by battery acid and nitric acid, right? But they are quite different, obviously. You can drink one and the other one will do not drink. Most other juices and sodas and drinks are on the slightly acidic side, right? They are in the middle acidic range. Some other cleaning supplies are often basic, up here and here, right? So fairly interesting. In healthcare, hopefully everything that you deal with besides possibly gastric juices should be in this nice middle range of pH. I threw in another question. I think we know this one pretty well by now, right? Blood pH between 7.35 and 7.45 is known as physiologic pH, although you could probably get away with calling it any of these three up here as well. All right, let's practice actually doing some calculation here. Let's look at orange juice and this cool orange given a thumbs up. Drinking orange juice, I don't know how that works out. An orange drinking orange juice, is that okay? I don't know. Anyway, so let's say this is the H3O plus concentration, 1 times 10 to the negative 4 moles per liter. What is the pH? So I guess we can do the first one together and then have quite a few more here that I'll let you do on your own. So if we know H3O plus, right, we're going to take the negative log of H3O plus concentration. So the negative log of 1 times 10 to the minus 4, and it's moles per liter. That would give us simply a nice 4.0. as the pH. What is the OH minus concentration? Right? Remember this equation as well. And OH minus is 10 to the negative 14 over H3O plus. So in this case, right, 1 times 10 to the negative 14 over 1 times 10 to the negative 4, and that will give us 1 times 10 to the negative 10. If you plug this into your calculator and you get 1 times 10 to the negative 18, just be careful, you're doing something wrong. It thinks you're multiplying by this instead of dividing. But as a check, always remember that the exponents should add up to negative 14, and indeed they do here. That is, as long as the values in the front are 1. And that won't always be the case, but when it is, you can check it. Okay, number 2. What's the pH of orange juice if the H3O plus concentration is 1 times 10 to the negative 3? And what is the OH minus concentration? So you can plug it into your calculator. Maybe you can just see it by now. That the pH is going to be equal to 3, and the OH minus concentration is 1 times 10 to the negative 11 molar. And you can always use the equations, right? Okay, the last example here, I can't even do this in my head. It's easy when this here is 1, but of course that's not always true. So what is the pH if H3O plus concentration is 3.2 times 10 to the negative 4? Now we will probably need our calculators. And we can simply plug in our value. And before we do, let's think about what this number should be. Where does 3.2 times 10 to the negative 4 fall relative to 1 times 10 to the negative 4? Well, it's bigger, right? But it's smaller than 1 times 10 to the negative 3. So it's somewhere in between. And remember, this pH was 3, and this pH was 4. So we should expect to get like a 3 point something pH, somewhere between 3 and 4. And indeed, it's 3.5. Your intuition might lead you astray sometimes when we're dealing with negative exponents and logs and things like that. So I advise, always calculate if you can. And then again here, what is the OH minus? That's also not quite as simple to do in your head. We can't just add up the exponents this time because we have values in front. And so 1 times 10 to the negative 14 divided by the H3O plus concentration, which is 3.2 times 10 to the negative 4. And we get 3.1 times 10 to the negative 11. And there's a good slide to have on hand, right? And again, I noted this before about how these numbers scale relative to each other. Okay, so if we go back, let's look at normal physiologic pH. So we've learned how to calculate pH from the H3O plus concentration. Now, given pH, how do we calculate the H3O plus concentration? How do we go the other way? Right? And here you need to have some memory of logs from math class, that we want to take the inverse of a log. And to do that, right, we said the log is what do we have to raise 10 to the power of to get this number. So to do the inverse is simply to take 10 raised to the power of that answer. So here's the second equation. H3O plus is equal to 10 raised to the negative pH. And the negative is because there's a negative sign here, right? So it's basically doing the inverse and getting it back out. So, like, what is the hydronium concentration for perfectly physiological pH? 7.4. We can take 10 caret, raised to the, it's not, we don't want to use the times 10x or something, or 10x button. That's more for exponents. Here, you can just use the caret. I mean, it'll work if you do it this way, but it's not technically correct. So 10 caret negative 7.4, and we get a value of 4.0 times 10 to the negative 8, which seems about right. It's less acidic than pure, so it's slightly less than 1 times 10 to the negative 7. So perfectly physiologic pH, blood has an H3O plus concentration of 4 times 10 to the negative 8 molar. And I don't have any more questions doing this kind of calculation here, but you can find more practice in the text and on the homework. Okay, so that actually wraps up this section. We introduced the relationship between H3O plus and OH minus, where we see that their product is equal to a constant. And this comes from the auto-ionization of water as well, so that even pure water has the ions in it. And then we saw the relationship between pH and H3O plus, where pH is equal to the negative log of H3O plus. And the inverse is that H3O plus is equal to 10 raised to the negative value of the pH. And that's it. Here is just a cool slide from Compound Chem, a website that has fun infographics. And pH is very quantitative, but there are also many qualitative ways of finding pH besides quantitatively measuring it. And one is with indicators, which are typically just different colors. There's one called a universal indicator that goes all the way from dark red for acids through like green all the way to like purple and then dark for bases. It's like basically the entire rainbow. And I think this is why, anytime you see textbooks, acids are always red, bases are always blue, because the universal indicator is like that. It's just a chemical that takes on different color forms at different pH values of solution. So it's really quite cool. But yeah, this is just a good slide to end on. So this wraps up 9.2, and make sure you do the post-lecture questions and start looking at some of the homework. And in the next section, we will look at what happens when an acid and base come together to react.